Hello dear students, welcome back to my class. Okay, so we are discussing about the compound microscope, right? Okay, so continuation from the previous class. Okay, we have already derived till m equal to m naught. M naught represents the magnification for objective, right? And me represents the magnification for eye lens. Okay, so now, okay, from the diagram we can see that what is the definition of magnification? It is nothing but for the lens ratio of image distance to the object distance. So for the objective, so I can write here what is the image distance for the objective. This is the image A dash B dash. So V naught represents the image distance and U naught represents the object distance. So I'll write here V naught divided by U naught. Okay. For again magnification for what? Eye lens. For the eye lens, see, as I already told you, right, this A dash B dash is working as object. So distance of this A dash B dash from the optical center will represent what? Object distance. So here object distance is what? UE. Okay. So next for again this here we need what? Image distance. So image distance for this eye lens. So where is the image? This is A double dash P double dash and the distance is nothing but here. Okay, we can represent this as UE. Okay, so I'll write here sorry VE here, right? VE equal to D. Okay, so this is the expression. Now we have to modify this expression a little bit. Okay, I'll modify this expression a little bit. Okay, so let's give this numbering. Say this is 1. Okay, now look here. So why we have to modify this equation? Because we have to find the image object distance for this eye lens. Because now you see when the image is formed by this objective, image can be formed anywhere between the focus of the eye lens and the optical center. It may be here, here or here. Okay, right, anywhere. It may be at the pole. Anywhere the object distance will vary for eye lens. So to find the object distance we have to use the lens formula. Okay, so let's use the lens formula and let's find out the value for this UE. Okay. Okay, so from the lens formula, right? From lens formula you can write, or lens formula for eye lens. So I can write 1 by VE, this is V, okay, minus 1 by UE equal to what? 1 by FE. We need the value of 1 by UE. So I'll find the value 1 by UE should be 1 by VE minus 1 by FE. Okay, so from the equation 1, let's put the value. So 1 implies M equal V naught divided by U naught equal. So here I can write VE, I'll just modifying little bit. Okay, VE into 1 by UE. If I again multiply by VE multiplied by 1, it will again give the expression VE divided by UE. Now let's put the value of UE. So M V naught U naught. The value of UE is given by 1 by V minus 1 by FE. 1 by FE, right? 1 by UE or 1 by VE minus 1 by FE. Okay. So now let's simplify it. So this is M equal V naught U naught. So if we multiply VE into 1 by VE, VE will cancel out. So I can write here 1. Okay. Minus, if I multiply this VE multiplied by 1 by FE, I can write VE divided by 1 by FE. Okay. So this is the expression. Now we'll use our sign convention and we'll put the value of VE. So here you have to write by applying sign convention, or you can write by applying new Cartesian sign convention. So what is VE? What is VE? Dear students, as you can see, what is the means? We have adjusted the object distance in such a way that the image will form at least distance of distinct vision. So the final image is at where? Least distance of distinct vision. So here the value will be D, and the sign on this side, it means this is on the negative side. So this is minus D. So let's put the value here, the final value M equal V naught divided by U naught into minus, the value is what? V equal to minus D. So I am putting minus D here. So this is VE. So now V naught U naught minus minus plus. So D by FE. So that is M. That is M. So what we got? M equal to V naught divided by U naught whole into 1 plus capital D divided by Fe. So this is the expression for magnification of compound microscope when the image is formed at least distance of distinct vision. Okay, let me repeat the definition for magnifying power. It's same for each and every optical instrument. It is the ratio of angle subtended by the image at eye, okay, to the angle subtended by object at eye, okay, when both are placed at least distance of distinct vision. Okay, okay, so it's already done. So let's move on for that one, when the image is formed at infinity. Okay, now dear students, there is this is very simple. This is very simple for that one, for compound microscope. Okay, so now you look here. So what we have to do, if we want the image at infinity, you have to adjust this object distance in the objective side, okay, in the objective side, in such a way that the image by the objective will form at focus. Means, as I draw here, if I draw here, okay, if I draw here, that image must form at exactly at the focus of the focus of what? Eye lens. Is it clear? So focus of eye lens. Okay, now you look here, when now this is working as an object for eye lens, right? So when the object is at focus, the image will form at infinity. Image will form at what? Infinity. So this is very simple, right? Diagram is not necessary. Okay, but let me give you the expression. What happens if the image is formed at infinity? Expression for magnification. So I can write m. So it's not going to change. So we can write again v naught u naught whole into, okay. So here, so what happens? So where is the main expression? This is the main expression, right? V naught u naught divided by VE divided by UE. So at this condition, so as we know, so this will be what? We can write this is what? F E, and this becomes D. Okay, this is the expression for magnifying power when the image is formed at infinity. Image is formed at infinity for microscope. This is V naught u naught into D divided by F E. Okay, so if you have any doubt how we calculated this value D by Fe, you can again back to the simple microscope where we have already derived when the image is formed at infinity. So this is very simple. So you try this, okay. But dear students, this theory is very important, microscope as well as simple microscope for the coming year, means for your final exam, as well as whenever they ask in the exam, they ask the theory, at the same time they will ask you the numericals from this chapter. Okay, numerical means for this same topic. So you can practice 9.11 as well as 9.12. This is very important numerical for you. Okay, so this is about the optical instruments. So telescope, you please try to understand by yourself. You do self study, or when your school reopen, you can learn it, right? So this is how almost roughly 85% I have finished that one, ray optics and optical instruments, right? So next we will move on to another chapter. This is wave optics. So this is chapter 10. Okay, so dear students, our next chapter is what? Wave optics, right? This is chapter 10. So chapter 10 and chapter 9 both are like the weightage is 12 marks. Okay, so we can expect one long question from this part also. Okay, from chapter 10 we can expect one long question as well as one 3-mark question. Okay, as well as there is a 100% chances of numericals will be asked from chapter 10. Okay, so now let's start with the chapter 10. So what is chapter 10? Chapter 10 is about the wave optics. This is about what? Wave optics. So in chapter 9 we are discussing the ray of light, assuming that it is particle nature, means light travels from one point to another in a straight line. But when we say this is wave, as you can see, the light is now wave like this, right? Wave. Okay, but you have to mention one point: the wavelength of the light is very small. It is ranging from 400 nanometer to 780 or 740 nanometer, right? Okay, so now look here. So we are assuming this is wave, light is wave nature. Okay, but there are so many theories given by the different scientists. So first page is about the history, about the so many different theories given by the different scientists. Okay, so first theory was given by Newton, which we call Newton's corpuscular theorem, right? We call what? Newton corpuscular theorem. Okay, that theory was given by Newton in the year of 1673. 1673, Newton corpuscular theorem. In this theorem, Newton assumed that light has what? Particle nature. Light is what? Particle nature. So because Newton is a mechanics guy, right? He entirely based on the mechanics. Okay, so you can say that when the light, we assume the light is a particle nature, Newton only explained the reflection as well as the refraction phenomena, but he failed to explain so many phenomena like diffraction, interference of light. Okay, so he only explained reflection as well as refraction, but he failed to explain so many phenomena shown by the light. So this theory is not that popular. Okay, but again in the year of 1675, in the year of what, 1675, another theory on light was given by Heisen, or you can say Huygens. Okay, you can say Huygens. Huygens. Okay, so I used to pronounce it Heisen. Okay, Heisen's wave theory of light. Okay, so this is the theory we have to study now. Okay, because the Heisen is the first scientist that he assumed that light as wave nature. So by assuming the light as wave nature, he explained reflection, refraction, as well as interference, diffraction. Okay, he four phenomena will be was explained by this Huygens or Heisen, but he failed to explain the phenomenon, that polarization of light. He failed to explain what? Polarization of light. Okay, so next theory. Okay, next theory was given by the different scientists, where he explained all the theorem like reflection, refraction, reflection, refraction, as well as interference, diffraction, as well as polarization. The name of the scientist was Maxwell. The name of scientist what? Maxwell. It is in the year of around 18th century. Okay, around what? 18th century. It's explained by Maxwell, but Maxwell fails to explain the absorption as well as emission of light. So Maxwell failed to explain absorption as well as the emission of light. Okay, again later on another theory was given by Albert Einstein. Albert Einstein in the year of 1905. In the year of 1905, where he believed that light is an electromagnetic wave. Light is what? Electromagnetic wave. With this assumption, he explained everything, almost polarization, right? Polarization he explained, absorption, emission he explained, as well as he explained the photoelectric effect shown by the light. Okay, again he proved the new phenomenon, or he showed the new phenomenon shown by the light, which is photoelectric effect, for which the Albert Einstein he awarded the Nobel Prize. Okay, so this is all about the history. Okay, so but if we assume the light as particle, we can explain some of the theorem, but if we assume the light as wave nature, we can we can explain some different theorem. Okay, but in both the cases are valid. We have to consider sometimes light as a particle, and have to consider light as what? Wave nature. So that's why it has come to conclusion that okay, light has dual nature. Light is what? Dual nature. Light is what? Dual nature. So in this today's world, in modern theory, we believe that light has two nature. This is particle as well as wave, which is known as the dual nature theorem. Okay, that's what now we are believing in this century. We are assuming light has dual nature. Okay, so this is about the history, dear students. You go through the first page, you will get everything. Okay, ER and all these things. Sometimes they might ask you MCQ questions. Okay, MCQ questions. So first, as I told you, we will discuss first the Heisens Principle, right? We will discuss Heisens Principle, where Heisens believed that light has wave nature. Okay, so before discussing the Heisens Principle, let's try to understand some keywords. This is wavefront. That is what? Wavefront. That is what? Wavefront. So let me tell you what is wavefront. Okay, so wavefront are the locus of particles. Wavefront is what? Locus of all the particles in the of the medium. Locus of all the particles of the medium which are vibrating at the same phase. Which are vibrating at what? Same phase. Okay. Suppose this is a source. This is what kind of source? So this is the point source of light. Okay. So from here the wave emanating like this, right? Wave is emanating like this. Okay. So many waves, because infinite number of light waves will be emitted by a source. Okay. But here the diagram is not perfect. But if I joined all the particles which are vibrating in the same phase, vibrating in what? Same phase. So suppose this, okay, diagram is not accurate, but I am just to make you feel. Okay, if I draw the locus of point of all the particles vibrating at the same medium, I will get the wavefront. Here I will get the spherical wavefront, because this is point source. Is it clear? So this is how we will get so many wavefront like this, is infinite number. Okay, when this is point source, we will get spherical. In 3 dimensions, you will get spherical wavefront. Okay, so what is wavefront? It is the locus of all the particles of the medium which are vibrating at the same phase. Okay, this is about the wavefront. Okay, now let's discuss what is Heisens Principle. Okay, so suppose here I am taking one point source. This is what? One point source. So, its wavefront will be spherical like this, spherical like this. Okay. So, according to Heisens principle, every point on this wavefront, suppose if I consider here one point means one particle, every particle on the wavefront will the new source of wavelets like this. If I consider another particle, see here also will get different wavelets. Okay. Is it clear? These wavelets are called secondary wavelets. So, if you consider here, you will get, okay, it is not that particular, here also you get everywhere, okay, everywhere. That is why when we on the light, okay, light will, light will spread out everywhere. That is why we can see, suppose you can see the any object from every side. Okay, this is how we will get the different wavefront. Okay, so now, so Heisens principle states that every point on the wavefront is a new source of disturbance which propagates with the same speed as the original source. Is it clear? And then if I draw the tangent, of these wavelets, suppose I am drawing the tangent, and I will get the new primary wavefront. So, if I draw the tangent from these spheres, I will get what? New primary wavefront. So, what you have to remember when you go through the book, so the whole theory is every point on the wavefront is a source of new disturbance which we call secondary wavelets. If we join the tangent of the secondary wavelet, we will get the new wavefront which is again a primary wavefront. Is it clear? So, this is about the Heisens principle. Okay. So, now by using the Heisens principle we can prove the law of reflection as well as the law of refraction. Okay. So, now let us try to prove the law of reflection with the help of Heisens principle. Okay, so before doing it, let us discuss the types of wavefront. Okay, so what is wavefront? As I told you, locus of all the particles vibrating in the same phase. So, depending upon the source, depending upon the source, there are three types of wavefront. Okay, first it is called spherical wavefront. It is called what? Spherical wavefront. Spherical wavefront. Okay, when we take the point source, say bulb, when we take the point source, we will get the spherical wavefront. So, you can write the wavefront produced by the point source is called what? Spherical wavefront. So, say this is the point source and these are what? These are the wavefront, all are spherical. Okay. So, now next is cylindrical wavefront. Next is what? Cylindrical wavefront. Cylindrical wavefront. Cylindrical wavefront. So, what is cylindrical wavefront? When the source of light is linear source. What? When the source of light is linear source, you can assume it is a slit, right? Or you can assume this is a rod light, right? Tube light. Okay. So, when the source is linear, we will get what kind of wavefront? We will get cylindrical wavefront. Suppose, so this is a linear source. This is what? Linear source. Okay. This is linear source. So, our wavefront will be like this. Okay. Wavefront will be what? Cylindrical. Okay. Just trying to show you. Okay. So, this is how from every side of the source the light will emanate. Okay. So, what is cylindrical wavefront? When the source is linear, we will get the cylindrical wavefront. Okay. Now, next is plane wavefront. Next is what? Third number we have plane wavefront. I am writing in short WL. Plane wavefront. Okay. So, when we observe the spherical wavefront or cylindrical wavefront from the very far distance, means when the source is at infinity, whether this is a point source or whether this is a linear source, okay, then we will see the plane wavefront. Means the condition of plane wavefront is when the wavefront is observed from very far distance, means from the infinity. Suppose when you observe the wavefront coming from the stars, this will be visualized as what? Plane wavefront. Is it clear? Okay. So, okay, this is about the wave. This is just an introduction, dear students. The main chapter starts from the Heisens principle, right? From Heisens principle. After completing Heisens principle, we will be getting interference of light, after the diffraction and polarization, and we have what? Resolving power. So, in later class, means next class, I will discuss one by one. Okay. So, okay, bye dear students. You keep practicing all these things, and especially for the prism, you please recorrect it. You place minus in place of plus. Okay. Thank you.